Assalamu alaikum wa rahmatullahi wa barakatuh. Hello everyone. Welcome to Lecture 3, Organic Chemistry 2. Today we will continue on Chapter 1, Conjugated Bi-Systems and Pericyclic Reactions. In the previous lecture, we talked about Diels-Alder reaction. Today we will talk about molecular orbital description of cycloaddition reaction. Well, frontier molecular orbital FEMO approach deals with the highest occupied molecular orbitals, HOMO, and lowest unoccupied molecular orbital, LOMO. They are known as frontier molecular orbitals. A theory stated that the occupied orbitals of different molecules repel each other. The occupied orbitals of different molecules repel each other. The occupied orbitals of one molecule and the unoccupied orbitals of other, especially HOMO and LOMO, interact with each other, causing attraction. The molecular orbital picture of the pi system. Recall we have ethene with 2p orbital with 2 electrons. These 2 orbitals build up 2 molecular orbitals, pi and pi star. When we fill first pi with 2 electrons. That's why we call this as HOMO, highest occupied molecular orbital. Pi star is empty, we call it LOMO, lowest unoccupied molecular orbital. In 1,3-butadiene system, we have 4 p electrons, and these orbitals build up 4 molecular orbitals: psi1, psi2, psi3, psi4. We fill the psi1 with 2 electrons and psi2 with 2 electrons. That's it, 4 electrons. That's why we call psi2 HOMO and psi3 LOMO. Okay? The reactivity of conjugated polyene could be understood by focusing on their frontier orbitals, HOMO and LOMO. This approach, called frontier orbital theory, was first advanced in 1954 by Kenichi Fukui at Kyoto University, Japan, and he was a co-recipient of Nobel Prize in Chemistry in 1981 with Ronald Hoffman for his work. Let's apply the frontier molecular orbital theory to the 4 pi plus 2 pi cycloaddition reaction, Diels-Alder, in thermal condition. Well, the diene psi2 is a HOMO, and it has 2 different terminal faces. As we can see, here is red and here is blue. Okay, here is red and here is blue. Now, the LOMO of the dienophile ethene also has 2 different faces. Here is red and here is blue. If we put the diene up and the dienophile is in beneath, then the orbital will have symmetry allowed interaction, blue blue, red red, right? And we call that symmetry allowed synchronous overlap. Note that the symmetry of the interacting orbitals permits synchronous bond formation, while the p orbitals of the pi bond become sigma bond in the product. When the p orbital interact with another p orbital, head to head they form sigma bond. Diels-Alder's Endo rule. Endo mode of addition is usually preferred to exo addition due to secondary orbital overlap between dienophiles activating substituent and the diene. Well, look at the HOMO of the diene. HOMO of the diene beside 2, as we can see here, if we say here is red, so red, red, blue, blue, that is for the phase. Okay, here is the phase. Red, red, blue, blue. The terminal are 2 different phases. Now, look at the LOMO. The LOMO will be here blue, red, red, blue, blue, red, red, blue. If we have here is a ethene dienophile, and we consider this as a extension or the substituent activating this dienophile, we will see that here blue, blue, so we have here overlap, successful overlap. Here and here we have successful overlap. But we can see clearly that we have here interaction and interaction. This interaction, we call it secondary orbital interaction, which lower the energy of the transition state. And we have to notice that this is endo orientation. Okay. Now, if we have this group on the dienophile, but in exo orientation, endo means that it is going to the biclouds, inside the bicloud of the diene. Here is far away, there is no interaction then. So the transition state in this case is higher in energy. Endo will be kinetically favored with low activation energy, and the reaction will go this way. So we will find that the transition state, this double bond is facing the diene underneath. Okay, and the product will be 4-ethinyl cyclo-1-ene. How to draw the Diels-Alder products with stereochemistry. We consider here the diene. This group, we call it outside group. And the group here, we call it inside. So this is inside, this is inside, and this is outside, outside. For the dienophile, the group on the left will be endo, and the group on the right will be exo. So this is exo, this is exo. Now, the group inside will be up. That's the one inside. The group outside, these groups will be behind the plane. Endo will be behind the plane. Endo. Exo will be out the plane. So, once again, how we get these two molecules together. The diene in the up, okay, diene up. And then we put underneath it the dienophile in a way that the exo will be this way. This is endo, this way. And the exo are on the other side. When they interact, exo goes up, as well as the two groups inside. These two groups go up. On the other hand, the endo go down, and the outside groups go down. And we end up with this enantiomer. Okay? But remember that you have another enantiomer. It's racemic nature. Draw the product of the reaction. Here is the diene, and here is the dienophile, alkene. We have phenyl, we have this alkyl group. This is much more deactivating group, so this one will prefer to be endo in the transition state. The carbonyl endo approach, and the product will be this. Remember that this is inside, this is exo, and this is endo. Now let's see how it looks like. This is up, this is exo up, this endo down, and the yield here is 67%. If the carbonyl is exo, so the double bond in here, and this is exo, and the phenyl is endo, then we end up with that this is exo, so it's up, and the phenyl is endo, so it's down, and this will be minor 33% yield. Draw the product of the reaction of trans-trans 2,4-hexadiene with methyl propenoate. Show stereochemistry clearly. So when I draw it, I draw the trans-trans 2,4-hexadiene this way. But I have to rotate around single bond to get this molecule in what we call it S-cis, trans. So that's right. React now with methyl propenoate. How we put these together? Again, this is the dienophile, and this is the withdrawing group here, which activates the reaction, but it has to be in endo. So we get this double bond, with the electron withdrawing group Endo in the transition state. Remember, this is the methyl group is out and this is outside, both of them, and this is Endo. So when this is outside, means that below the plane, and the Endo is below the plane. So what is the product? The product will be below the plane, below the plane, below the plane. All right? Predict the products of the following Diels-Alder reaction. Here is the diene and here is the dienophile. So we have to identify the location of high electron density in the diene, and the electron deficiency is in the dienophile. And we put these sites near each other and then we draw the transition state. Now, here is this one diene. The diene here, the electron density will locate on this carbon. Here is the dienophile, the resonance showing that this is electron deficient carbon. So we get this carbon near this carbon. So we get this carbon, which has a negative, I put it here. Okay, and here is the electron deficiency site. So these two sites will interact to give this product. This will be up. These two are on sp2 carbon, so it's planar. There is no up and down. Let's see this diene and this dienophile. Which carbon has higher electron density? Of course, according to the resonance structure, this carbon will be high in electron density. The dienophile, the resonance showing that this carbon will be electron deficient. We get this one near this one, and the interaction will take place between this. According, here is Endo, down, down, and here is outside, will be down. And this is the structure of the product. Here, once again, the electron density is showing that this one side, this side, will be electron rich. And again, this side will be electron deficient. We get this side together. So this side will be with a negative side in electron rich side, and the transition state. This is Endo, this will be down. This methoxy group on sp2 carbon, there is no up and down, and that's it. Okay. When we have this molecule, this group is pushing, methyl group, so the electron density will be on that carbon higher. Cyano is electron withdrawing group, deficiency on here higher. So we had to get these two together, this and that. But remember that you have to put the cyano in Endo. So the cyano is Endo, so it will be down. CH3, this one is outside, so it will be down. This one is on sp2 carbon, so there is no up and down. and that relation between these cis, they are on the same direction. Okay? 2 plus 2 cycloaddition reaction. Let us use the frontier molecular orbital approach to determine whether the following reaction is possible. Ethene, two molecules of ethene react together to form cyclobutane. Thermally, if we look to the ethene molecular orbital, we will find that the pi bond with 2 electrons is HOMO, while pi star will be the LOMO. Now, let's allow the HOMO and LOMO to interact. HOMO and LOMO to interact together. See here, 2 red, the same face. Here, the 2 different faces. So when you have here, approach the HOMO and the LOMO, okay? So these faces are the same. Here, blue with blue, allowed, fine, there is an interaction. But in this case, these are 2 different faces, there is no interaction. Faces do not line up, symmetry forbidden. When we try to align these frontier orbitals, we find that the faces of the molecular orbital does not overlap. This reaction is therefore symmetry forbidden, and the reaction does not occur under thermal condition. Now, 2 plus 2 cycloaddition can only perform with photochemical reaction. Photoexcitation will take one of these electrons in HOMO and transfer it to the LOMO, so we'll have a new HOMO. This is a new HOMO with 2 different faces. They are not the same face, right? Red and blue. Now, if we get the excited state HOMO with 2 different faces, with the LOMO of another molecule in a ground state, so blue with blue match, red with red is matching, faces now line up, symmetry allowed. So this 2 plus 2 reaction takes place under photochemical condition. Show that the cycloaddition of 2 butadiene molecule to give cycloocta 1,5-diene is thermally forbidden and photochemically allowed. One more time here, we have Psi1, Psi2, Psi2, red, red, blue, blue, okay? Red, red, blue, blue, that's HOMO. LOMO, blue, red, red, blue, blue, red, red, blue, matching. These 2 are not matching. Faces do not line up, symmetry forbidden. So this reaction will not go under thermal condition. Recall once again the 1,3-butadiene in the ground state has 4 molecular orbitals. Psi 2 is HOMO with 2 electrons. Look at the faces here. If we say this is red, so it's red, red, blue, blue, and the LOMO will be Psi 3 with, if we say that here is blue, red, red, blue, so two inside the same faces, and the outsiders are the same face. Okay, now if we irradiate this molecule with UV light, we take one of these electrons on HOMO and transfer it to psi 3. Now psi 3 became a new HOMO. So looking at these two faces are the same and the two inside are the same. So if you start here with blue, blue, red, red, blue, and that will be HOMO of the excited molecule. The LOMO of another molecule in the ground state will be the same type: blue, red, red, blue. Let this new HOMO approach to the LOMO, okay, one up and one beneath, and approach them. We will find that blue matches with blue, same face, and these two are on the same face. So faces line up, and the reaction 4 plus 4 is photochemically allowed. Show how Diels-Alder reaction might be used to synthesize the following compound. Here is a double bond, right? So the one in here will be number 1. This is number 2, 3, 4. So this is number 4. We cut in here, we cut in here, and we get, here is our diene, double bond in here, double bond in here. Okay, and then the dienophile will be in here. That's the dienophile. Here, for this molecule, 1 and 4, cut, cut. Here we have, this is our diene, and since this chlor is up and this chlor is down, so they are trans 1,2-dichloroethene as the dienophile. 1, 4, cut, cut. Here is our diene, and our dienophile will be acetylene. Okay, triple bond. For this particular molecule, again, here is double bond, so 1 will be here. Let's see, 1 in here, 4 in here, cut in here, cut in here. Here is our diene, and our dienophile will be double bond in here. Here we are. For this one, well, here is 1, here is 4, cut in here, cut in here. Here is our diene, and here is our dienophile. After we cut, we add double bond in here. That's it. I draw it this way, so that's dienophile, and this part, which is electron withdrawing group, will be endo. Okay. For this particular molecule, okay, here is 1, here is 4, cut in here, cut in here. They are on the same side down, so they are endo. So when I put that is the diene and dienophile, again I draw it this way here, and these two electron withdrawing group facing the bi system in endo orientation. Here is Diels and Alder, who obtained the Nobel Prize in 1950 for their fabulous reaction to form cyclohexene. See you next lecture. Bye bye.